Integrated rate law is an equation that expresses the concentration of reactants as a function of time. From this equation, we can determine or find how long does it take for a reaction to occur, meaning that we can determine the time required for the initial concentration of a reactant to be reduced to some final value. Secondly, how much remain after a given time, meaning that we can also determine the concentration of a reactant remaining after some times after the reactions takes place. Okay, and then thirdly, what concentration was present initially in the reactions, and overall of the reactions are depends on the overall order of the reactions. It is either zeroth order, first order, or second order. For zero order reaction, when A becomes the product, the initial rate for this reaction is equal to K times concentration of A to the power of 0. Anything to the power of 0 is equal to 1, so 1 times K equal to K. The rate also can be negative the change of concentration of A divided by the change of time. When we substitute the K into this formula, we can get the formula here, then we rearrange and integrate the formula. We can get the final formula for zeroth order reaction is AT equal to negative KT plus A naught. Okay, so when we relate this equation to a straight line graph, or we want to plot a graph AT against T, we can relate the equation to Y equal to mx plus C. So Y is referred to the AT, the Y axis, and negative K is the gradient, T to X axis, and A naught is the interception at Y axis. So this is the graph for zeroth order reaction. For first order reaction, when A becomes the product, the initial rate for this reaction is equal to K times concentration of A to the power of 1 because of the first order. And the rate also can be negative the change of concentration of A over the change of time. So when we substitute Ka into this formula, we can have the formula here. Then when we rearrange and integrate the formula, we can get the final formula for this first order reaction is ln AT equal to negative KT plus ln A naught. When this equation we relate with the straight line graph, which is Y equal to mx plus C, we can say that ln AT is y-axis, negative K is the m or the slope or the gradient from the graph, T is the x-axis, and ln A naught is the C, the intersection at y-axis. So we can see the overall graph here for first order reaction. For second order reaction, when A becomes the product, the initial rate will be K times concentration of A to the power of 2. So the rate also equal to negative change of A over change of T. When we combine both of the equation, we can get the Ka to the power of 2 equal to negative change of A over change of T. When we rearrange back the equation and integrate the equation, we can get the formula for second order reaction is 1 over AT equal to 1 over A naught plus KT. This one is when we relate to the straight line graph, we can say that this is y-axis. This one is the C value, the interception at y-axis, and K is the slope or the gradient, T is the x-axis. So this one is the graph for second order reaction. Half-life of a reaction is defined as the amount of time taken for the concentration of a reactant to decrease to half of its initial value. In this case, we change the T equal to T half and AT equal to A naught over 2. Okay, because the reactant is to decrease to half of its initial value, so divide by 2. When we substitute this formula into the original formula of zeroth order reaction, first order reaction, and second order reaction, we can get the T half for the respective order is for zero order is A naught over 2K, and T half for first order is ln 2 over K, and T half for second order is 1 over K times A naught.